So let's do a review of what we learned last year about the atom and our different models of the atom. Here we have a diagram that shows the progress made. So in Dalton in about 1800, he viewed the atom as a single indivisible particle. That's what atom means. Atomos would be you couldn't divide it. And then from there, J.J. Thomas came up with a plum pudding model of the atom. And then from there, Rutherford concluded that the atom has an infinitely dense but also infinitely small nucleus in comparison to the size. So there's nothing drawn to scale there. And then finally Bohr, his big contribution, this is something that you are going to want to remember, is that he concluded that each of the orbits that the electrons are in, they're quantized. They can only be in certain orbits that he represents with simple whole numbers. And then finally, we're going to conclude by looking at Schrodinger's quantum model. So let's have a look at this. Dalton's idea was that all atoms, they're composed of indivisible particles. All matter, I should say, is composed of individual particles called atoms. And one of the other conclusions that he draws is that all the elements of the same element, all the particles of the same element, they have exactly the same properties. So if you have one atom of carbon, it's going to be identical to any other atom of carbon that you run across. It will chemically react the same. And of course, it turns out to be true that one atom of carbon reacts identical to any other atom of carbon. And chemically, they're the same, but they don't actually have to be the same as far as the nucleus. Let's have a look at that. William Crookes, what he discovered was this, that if he bombarded atoms with high energy, that he could actually drive off particles. And he called these particles cathode rays. And what that showed is that something on the atom, and they didn't know what it was, it could be knocked off the atom. And they could tell that it was negatively charged because it moved toward a positively charged anode. So here's another picture. This is an actual cathode ray tube. You have a picture of a target that they place in there. And what we learn is that as those cathode rays come, that we know they're particles because they form, that they're stopped at the edge of that target and they form distinct lines. So they're not making their way through it. So they're particles. That was the contribution there. The next change was this. J.J. Thomson concluded that maybe the atom is like plum pudding, that it has positively charged matter that's just not particularly, it's not dense, it's just positive in some way. And those negative charges that you knocked off, those are going to be what we now know as electrons, those are the things that can be knocked off the atom. But there's one solid positive part of the thing, we're going to call that like the oatmeal cookie, and the oatmeal cookie remains the same. Sometimes you might knock off a raisin off of that cookie. And so Ernest Rutherford proposed to test that very thing because he didn't think that was true. So what he did was he knew that if the model was true, he should be able to bombard the atom with positively charged particles, and they wouldn't be deflected because there's no solid core to them. It's just kind of a general positive charge that makes up the atom, and the only things that could be knocked off or to be separated would be these negatively charged particles. And so he devised an experiment called the gold foil experiment. And he had a source of helium particles. So alpha particles are helium nuclei. It's got 2 protons and 2 neutrons. It's charged, doesn't have any electrons with it as it's emitted from a radiation source. And he just created basically a gun that shot these alpha particles at a thin piece of gold foil. And what he found was just what kind of everybody was expecting him to find if the plum pudding model was true, was that for the most part, everything just went straight through that gold foil. Matter of fact, 99.999% of all those alpha particles just went straight through. But when he moved the deflector to at positions of high angles, he noticed that sometimes, not all often, but sometimes he would get a hit on that deflector in spite of the fact that there's no reason. He wasn't even expecting anything to be down there because statistically he was accounting for all the alpha particles. Matter of fact, sometimes they even deflected at really, really sharp angles. And he was shocked. He said, this is like taking a cannon and firing at toilet paper and having sometimes that cannonball to bounce off the toilet paper and bounce right back at you. I have a video that I'd like to show you that it basically recreates this this experiment, and it's cool. Let's have a look at it.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom by comparison is very big, so it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Well, Rutherford, he produced what we now call the planetary model of the atom, or at least he made major contributions toward it. And what he concluded was, just as the video said, that the nucleus is in the center of the atom, and it is inconceivably small, but also inconceivably dense. So it's inconceivably small in comparison to the actual diameter of the atom. So this would in no way be drawn to scale. If this was the exterior of Rutherford's atom, the nucleus wouldn't even be as big as the little dot there it's kind of being represented drawing the arrow. I think that some estimates would be that if you had a nucleus the size of a nickel, let's say, that the closest orbiting electron would be about maybe a quarter of a mile away. So there's just a vast amount of empty space in between the first orbiting electron, n equals 1, and the nucleus of the atom. So that's the planetary model of the atom. It holds that the atom is mostly empty space, and the nucleus is dense and small in comparison to the size of the atom. So this picture is in no way drawn to scale. Well, after Rutherford's model of the atom, Niels Bohr wanted to do some testing about the atom as well. He knew that there were some interesting things that were showing up in spectroscopy, and he figured that the lines that were produced with spectroscopy actually had something to do with the energy of electrons being excited into higher orbits and then de-exciting down into lower orbits. So let's have a look at his approach. Here we have a hydrogen spectrum emission, just as you would see with the naked eye. The way this is produced is there's a vacuum tube, all the air is pulled out of it, and then a small amount of hydrogen is allowed in there. And then there's a charge that excites the electrons that are part of those hydrogen atoms to go to higher orbit levels and then cascade down. And as they do, they emit light. And so if we would look at the spectrum of hydrogen light, it would look something like this. Well, let's look at the full light spectrum to start with. So the full light spectrum has all of the color in it, all the way from our lower energy, longer wavelength reds to the high energy, short wavelength violets. If you look at the spectrum of hydrogen, the light as it produces, what you see is not the full spectrum, but you just see individual bands at repeatable intervals. They always had those bands at those same frequencies. And if you would look at that from an absorption perspective rather than an emission, you see those same bands, but they're just black. There's nothing there. So this shows that you have hydrogen that is absorbing a certain amount of light, and this spectrum here is a light emission spectrum. It shows that what it looks like when hydrogen is emitting those bands of energy. So what Bohr knew and laid out was this, that electrons, they only emit light when they are falling from higher energy levels back to lower energy levels, and then eventually they make it to the ground state. And that electrons are quantized because you always have the same bands of light, that it's not like you have this spectrum of the reds and then the blues, the greens, the blues, and the purples. They only emit light at certain places. So those electrons have to start at a certain n equals like 3 to 2 level, or and they stop at certain levels. They could fall from 3 to 2 or 3 to 1, or better yet, they could go from 5 to 4 or 5 to 3 or 5 all the way to 1. So there are an infinite number of these quantized orbits that exist. They just get closer and closer to each other as you increase the number. Show you a picture again of this band. This is one that we actually took when we built our own spectrometers. And it's just a picture of the light emission bands. Actually, that's not one that we built, because once again, that's of hydrogen. And we didn't have a hydrogen source. The term spectroscopy comes from the fact that these are very faint images, even though they stand out really stark to our eye there. And so specter, it comes from the word ghost, and spectrometer, it's the measuring of these faint image. That's where that comes from. So back to the hydrogen atom. So the hydrogen spectrum is this. You always end up, when you excite hydrogen electrons as they cascade down, this is all in the visible range. There are actually bands that occur in the UV as well as the ultraviolet, as well as the infrared range. But these are the visible ones. So you get one at 656.2 nanometers, 486.1, 434.4, or 434.0, sorry, and then 410.1. And his conclusion was that as an electron falls from an excited orbit down to a lower orbit, sometimes those electrons emit a green light. And that reflects the energy that was lost. And so from that wavelength, because this is light, if he knew the energy that was lost, he could describe the energy level that produced that green band, or that blue or that violet band. All right, here are some pictures of when we built spectrometers and just kind of looked at them. These were some of ours. Nothing special. You just see sunlight as a result of that. One of the other spectrometers that we built gave us a dual image, so you see it on both sides. This is the light source coming down the center, and we just have duplicate bands. We took a picture of some LED lights just to see, and they happen to be red, green, blue LED lights. So here, you don't actually have the full spectrum. You have an LED light that has a red, a green, and a blue, and that's what that looked like. Mercury vapor lights, if you would look at a lot of lights that are in some of the ballasts, above us. Actually, in my lab, I no longer have any mercury vapor lights, but they have a series of bands that reflect electrons that are cascading down. Another one will give you this is an example of a red, green, blue, just a color monitor, an old one that it was a red, green, blue emitter, and those were the bands that came out of that. All right, so our next slide is going to show you the light of the sun, and here we have some absorption bands, something that has to be in the sun in order to absorb these at these wavelengths. Here we have a hydrogen spectrum, which is our normal spectrum, and here we have a helium spectrum. And you can see there are bands that correspond to the absorption in the light from the sun. And that just shows that, the sun is mostly hydrogen that has gone its way to helium. Here's another picture of helium and then also of mercury. You can see the mercury bands. There's just thousands, it seems like. And I don't know if you have looked at this before, but we have a bulb that we can look at with our little, our goggles that we put on, and you'll see these bands. It's actually quite attractive. These are the helium bands again. So anyway, just a picture of the light emitted. And the whole point was this, that if you have a band, that has to represent an electron that was at a higher energy level, it's cascaded to some lower energy level, and it's emitted that band. And it's at a certain wavelength, and because we know that, from last year, we know that we could if we know the speed of light and we know the wavelength, then we can calculate the speed of light. We could calculate the frequency, and then from the frequency, we could calculate the energy. So anyway, that's how that went all about. All right, so quick review here. So the Bohr model of the atom. He recognized that there are negatively charged electrons that have an extremely small mass. I'm not sure how he concluded that the mass was, well, that's not true. Volume. We don't know about their volume, but it has to be a very small mass, such a small mass that it's not, doesn't even affect the mass of the atom, because all of the mass of the atom is bound up in the nucleus. And that those charged electrons, they travel in quantized orbits around the nucleus. They always do. So here's kind of a summary of his things. So The energy possessed by the electron in a hydrogen atom and the radius of its orbit are quantized. He calculated the values of these quantized energy levels using an equation containing just simple energies, which is really beautiful about this because, with just some simple algebra and using 1s, 2s, and 3s and 4s like you guys are going to do, you're going to be able to calculate the energy of an electron as it's cascaded from a higher to a lower energy level. On top of that, electrons, they move between orbits. We call it a quantum leap, or they jump. And here's a picture that you probably saw last year that shows an electron in a ground state, so that's n equals 1, being excited by some energy. It could be light or heat or whatever, and it pops that electron up into a higher orbit, in this case n equals 2, and that whenever that electron is no longer excited and it falls back down, it emits a photon. And that photon, the amount of energy, allows us to create to calculate the change in energy between the upper and the lower state. It's directly related to the wavelength and the frequency, and therefore the energy of that light. All right. So he introduced quantized electron energy levels in an atom. There were some problems with that, and this is where we pick this up in this module here, is that first of them, that hydrogen is the only atom that fits the Bohr model. Once you have more than one electron, just the math is too complicated. You really can't pull it off. So if we're going to use the Bohr model, it doesn't matter how many protons and neutrons we have in our atom, we can only have one electron in the orbit. And so as you're doing your calculations, you'll be able to calculate the energy level of that one electron, that n equals 1 level, and you can do it for any atom you want. You can do it for hydrogen, you could do it for helium, you could do it for lithium. I mean, you could do it for mercury if you want, but you have to drive off every electron except one, and it's got to be left in that ground state orbit. So the second thing that is a problem is that a charging body moved in a circular energy, it radiates energy. And what should have happened if we just have regular classical physics is that those electrons, as they lose energy, they should crash into the nucleus in a very short period of time. But of course, we all know that doesn't happen. So in the planetary model of the atom, what should happen is an electron, no matter how far away from the nucleus it is, as it is orbiting, it should be decreasing in its radius, and because it's losing energy, and then eventually it will fall into the nucleus. But that doesn't happen. And so Schrödinger devised a program, a mathematical equation that explains what the atom looks like, keeping the electrons in their quantized orbitals, and we come up with a quantum model of the atom. And this is what our module is dealing with. So in the first half of our module on the atom, you're going to play around with calculations based on the Bohr model. And then from there, we go to quantum mechanics. And the beauty is once you hit there, it's all a bunch of really great ideas and you get to see shapes. But you don't have to do any calculations because the calculations require phenomenal calculus. I don't know, like, 2 or 3 graduate levels of calculus to even perform. And that's certainly beyond me. So Schrödinger, what he did was he took the Bohr model of the atom and he said, all right, what's this? How can we talk about it if the Bohr model is, if we can't rely on classical physics? And so he comes up with the quantum model. And so we move from what we have talked about as the Bohr model now to a model that can only talk about the probability of an electron being in any one location. And we actually talk about it in terms of a density probability. And that's the quantum model of the atom. And all of our graphs, all of our drawings, all they are representations, mathematical representations of probable densities of an electron in a n equals 1 orbit, or an n equals 2, an n equals 3, and so forth. So the quantum mechanical model, instead of having orbits with a radius, now we're going to say the electron occupies clouds with specific energies and their orbitals. The shapes and size of these clouds are described by a set of quantum numbers. So n n equals 1, n equals 2, n equals 3, n equals 4. And then there is an azimuth number, then there's a magnetic subazimuth number, and then finally a spin number. So every electron could be defined in its location if you have all 4 of these numbers for that electron. And we're going to walk our way through that. So the first number is the principal quantum number. And this is the one that you see anytime you look at a periodic chart. It's the energy of the lowest, it's the ground state, it's the lowest energy level for an atom that an electron can occupy. The good news is that even though now we are talking about the quantum model, you already learned the energy level last year from the Bohr model. So n equals 1 in the Bohr model is the same thing as n equals 1 in the quantum model. Let's do just a little bit of review from last year on these energy levels and the n equals levels. Last year, we became familiar and comfortable describing the presence of an electron if we have an atom like lithium. Then lithium is going to have 1 electron in the 1s orbital as its valence electron. If we have an atom like aluminum, it's going to have 1 electron in its valence orbital that's a 2p, so it's in the n equals 2, but it's in the p orbital range, okay? And that's where its valence electron is going to be. And you're going to have all of the subshell electrons filled in underneath it. So if we look at sodium, for example, and if we want to know where the valence electrons are located in the sodium atom, we find sodium on the periodic chart, and sodium is located in the n equals 3 column right there, and it's going to have an n equals 3, and it's going to have 1 electron, and it's going to be an s orbital. So that's ought to be familiar to you. So you could go through and predict accurately where the valence electrons are for all of these other atoms. So calcium, for example, if you look at a periodic chart of the elements, you'll find calcium on the n equals 4. It's going to be right down in that level. And we know that it's going to have 2 electrons in that s orbital, and that's going to be its valence electrons. So go ahead and take some time just for review. Figure out where the valence electrons are for fluorine, bromine, lithium, titanium, silver, gold, silver, plutonium, and mercury, and just verbally go through and remember where their valence electrons are. I'll give you some time. You can stop this and then go through that. All right, back to it. So n is going to be the principal quantum number. In the quantum model, we assign a value of n to each electron. So for any electron that you're going to talk about, it's going to have some value of n. So for carbon, it has 6 electrons, and each of those has an n number. An example of that n number is this. You know that you have 2 electrons right here that are in the n equals 2. They happen to be p orbitals, but they're 2 electrons in the n equals 2. You've also got 2 electrons in the n equals 2 s orbital, and then you've also got 2 electrons in the 1s orbital. So that's what we mean by each electron has an n number. So we got 2 electrons with that 1 n number. I got 2 electrons with that 2, and 2 electrons with that p. Of course, now that doesn't uniquely describe the electrons, so we're going to need we're going to need a couple more numbers in order to uniquely describe them. So, just like in the Bohr model, these energy levels exist even if they're unoccupied. And so all we want to say about that is this. Let's say that you are dealing with a hydrogen atom. Well, if this is a hydrogen atom, if it has 1 electron that's orbiting around it in its ground state, it doesn't have any other electrons in upper orbitals, not in the n equals 2, 3, or 4, or 5. But if you hit that with some energy, you can knock an electron up into a higher orbital. And of course, after that is that the energy relaxes, they cascade back down, and a photon of light is emitted. But you just need to know that those orbitals exist, and they are predefined in their energy level based on the n value. All right, so the next thing we'll look from the n value, we'll go to the L value. This is the azimuthal quantum number. So last year we didn't assign any number to our s orbitals. We just called them s, p, d, and f orbitals. But this year we're actually going to give it a number so that we can deal mathematically with this. And s orbitals have an L value of 0. P orbitals have an L value of 1, and there are 3 of those p orbitals. D orbitals have an L value of 2, and there are 5 of those. And then F values have an L value of 3, and there should be 7 of those. So this L number, you start off with the N, and then you've got an L. It can only have either a 0, a 1, 2, or a 3. Actually, you can have higher orbitals, but when what we're doing, we're not going to get any higher than the D even. All right. The number indicates the shape of the cloud of the orbital. Now keep in mind that's just a mathematical conclusion, and it describes probable density of the location of the electron. So here the probable density in an s orbital is that it's going to exist in a sphere around it. Okay. In the p orbitals, the probable density is it's going to exist in the lobes. And remember that this is not 2 different orbitals. That lobe right there is one orbital, and it just exists at a different orientation to the axis of the deal. For L equals 0, that is an s orbital. So you can have an n equals 1 and an L equals 0. That would describe the electron in a hydrogen atom and a helium electron. That would be the valence electrons there, because they only have electrons occupying that s orbital. If you have an L equals 1, well, that's what last year we called p orbitals. So this is the L, the SPDF orbitals, and now we're just giving them numbers that are associated with them. If you have an L equals 2, that's describing d orbitals. If you have an L equals 3, that's describing f orbitals. And so that's what we're looking at here. And those are that's the connection between last year we talked about SPDF orbitals, and now we are just assigning them numbers. All right, let's just look at some atoms and kind of walk through and apply what we've already talked about. So if you have a hydrogen that has 1 electron, and it's in an s orbital, and that is the electron in that orbital. So n would be 1 for this electron, and because it's an s orbital, the L is going to be a 0, so it would be 1, 0, and that's just what that electron is. It has no other, it can't exist any other because it's just an s orbital. And so for helium, it's the same thing. We still have the n same value, n is 1, but our L value here is going to be 0 again because all s orbitals have a 0 L value. All right, let's look at carbon. So carbon is a little more complicated. Carbon both has an n equals 1 and an n equals 2 orbital, and it has these 2 electrons would both be described as n equals 1, L equals 0, and then we're going to add some other things to it. These 2 electrons are going to be described as n equals 2, L equals 0, and then they're going to add some more. But then finally we get to the p. This is n equals 2, L equals 1, and there are 2 electrons that are going to fall into that category. So that gives us an example of what it looks like with our n value and our L value. And once again, that's just examples of the shapes of these orbitals, L's. The next number that is associated with an electron would be the magnetic quantum number, the m sub L. And so for any 1s electron, n sub 1, L sub 0, it's only going to have a 0 for the magnetic quantum number because there's no other shapes that are associated with it. It's going to have two more numbers. It's going to have a minus spin and a plus spin, but other than that, all electrons that exist in these 1s orbitals are going to be defined as n equals 1, L equals 0, m sub L equals 0, and then we'll talk about the next two. But once we get to the p orbitals, now we have a location for different electrons. We know that we can put 2 electrons in each of these orientations. So now, if we have an n equals 2 and an L equals 0, which means we are dealing with the p orbitals, I have 2 electrons that can be in this minus 1, I have 2 that can be in this 0, and I have 2 that can be in this plus 1. And we'll describe how to differentiate those 2 that are in there in a minute, but that's what this m sub L magnetic quantum number is. If I have an n equals 3 level, okay, I am now dealing in d orbitals, and I can have an L equals 2, I can have a m sub L that would be anywhere from a minus 2 all the way to a plus 2. And each of these can have 2 electrons in them as well. And so it shouldn't surprise you that if we get all the way to the F electrons, our n level is 4, and our L level is going, n level is 4, our L level is 3, and each of these can have 2 electrons in them as well. The very last number that we're going to talk about is just the spin on these electrons. And this differentiates the 2 electrons that are in the same orbital. Any 2 electrons in the same orbital have to have opposite spin. And so whenever you fill orbitals, and we'll talk about the rules for filling them with electrons, you'll always differentiate 2 electrons in the same orbital. One will have a plus 1/2, and the other will have a minus 1/2 spin. So here are the rules when we are assigning electrons to orbits. First rule, we'll talk about the Pauli exclusion principle. No 2 electrons can have the same exact 4 quantum numbers. So 2 electrons can share 3 of the quantum numbers, but eventually one of them, if they're in the same orbital, one's going to have a minus and the other's going to have a plus spin. But that's our first rule. Any electron has a unique set of 4 quantum numbers, and the spin may be the only thing that's different from another electron, but at least that is as well. Hund's rule says that if you're going to assign electrons to orbitals, all orbitals with the same m sub L, they're filled with 1 electron before they receive a second electron. So what that looks like is something like this. So let's add electrons. Let's say that we're going to deal with a carbon atom that has 6 electrons. According to our rules, I can put 1 electron in this low 1s, and then I can put another electron in that 1s orbital before I fill any others in the higher orbitals. But both of those have to have opposite spin. So one will be a positive 1/2 and the other will be a negative 1/2. Then I can also put 2 electrons in the next lowest orbital, this 2s orbital, and the same way, they will have to have opposite spin. So usually the way we draw that is we have an arrow that goes up and then an arrow kind of that goes down, and that shows that we have opposite spins. So that's 2, 4. Now I'm going to add 2 more, 6. So here, our last rule says that if I put an electron in this azimuth L level of P, that I can't put 2 electrons in the same m sub L orbital. I need to separate them. So I would put 1 electron in this minus 1, and I could put 1 electron in this 0, and I run out of electrons. But if I had another electron, I would put it in this plus 1 category. And if I have more electrons to go, let's say I move from carbon on up, I can add my next electron. So if I have carbon, one here, one there, my next electron would be to add one to here, and then I go back and add them sequentially to those. And then once those are all full, if I have more electrons, I can move up to the S level of n equals 3. So that is how we fill the electrons. So go ahead and take some time, if you will. You can write an electron configuration for neon, for sodium, aluminum, argon, bromine, and whatever SB is. I've already forgotten. And you can kind of assign an address to it. You know, the address is the 1s2, 1s2, 2s2, to P up to 6 on that way. I'll give you some time to work through that. Actually, just pause this and do that. Well, let me say some things just in conclusion about the quantum mechanical model of the atom. This applies principles of wave mechanics to the atom. And like I say, the mathematics are pretty complicated on it, but it's very consistent. And it explains more satisfactorily than any other theory what's going on at an atomic level. And there have been no exceptions have been observed to this model. So it's very well tested, and even though we can't see this, matter of fact, it becomes increasingly more difficult to visualize, and so after a while we just talk about energy levels and we don't spend a whole lot of time trying to visualize it. It is a reliable model to describe the atom. And sometimes we need to talk about the model in this way. Other times the Bohr model works. Other times you might even just be satisfied with Rutherford's planetary model. On top of that, it's a mathematical in nature, and it keeps the quantized energy levels that were introduced by Bohr. So Bohr says that they're going to have these quantized energy levels, and sure enough they do, and that idea plays out mathematically in the quantum model of the atom. Well, that was quite a long review, about 42, 43 minutes of what you looked at last year, and then we got our feet wet at least again in this the module here in Module 2. All right, see you in class.